All right, so let's set the scene for you. What is the problem? Well, we have this uh, particular part that Chris identified. Now, what is it? Well, it's a fairly rare combination impeller slash inducer used for moving pump liquids. Don't have too many of these, but they are in stock, and Chris will need to make spare parts and manufacture them. Now, the drawings have been lost to time. We don't have any manufacturing format, but we do have the physical part, and we want to reverse engineer it. We're going to do that with scanning. To capture the outside, easy peasy, really easy. But to capture the inside, that's going to be a bit more challenging because the photos don't really do it justice. I'm sure Jonathan will talk about it later, but getting down into it, there's really not very much room. There's very limited line of sight. And currently, Exxon are passing on these opportunities to manufacture these with 3D printing because it's going to be too complicated, it takes too much time, and there's too many limitations with the technology. So that's the scene.
There we go. Okay. And as Sam said, there's a few different opportunities or options for doing something like this. One of them is line of sight scanning. You have a handheld scanner or even something on an arm. It's great for capturing the outer surfaces of the part accurately. You can do it relatively quickly. I think it was probably, 30 seconds or so just to scan the outside housing of this, but you're limited to line of sight. So especially with these deep crevices in this impeller slash inducer that we couldn't see, we also couldn't scan. The scaling might have not been obvious, but I could barely get my hand in there. So as we talk about some of the prep work that's involved, this thing is small. There's also possibly using CMM probing. So, we have a lot of customers that have CMM probes. Um, you are you still have some of those limitations. It can be a slow process to set up for a part. One of the benefits is if you have the same type of parts, you can set up your program, you can keep running it over and over, and it's great. It does require a bit of skill though. So it's a very accurate solution. There is a bit of degree of skill required, and then the internal geometries are still going to pose an issue. Are we able to get a probe in there? Are we required to get specialized tools to be able to do it? So some of the detail is going to be near impossible to capture.
Yeah, while you could do it, these probes are made of ruby last time I checked, so very expensive. Also, no guarantees it will work for the next part that has different internal geometry. So really, it's not a flexible enough solution for us. So that's why it's not the right one.
Yep. And then lastly, CT scanning is a solution that can be great for these types of things, but it is expensive. I don't have one available to me. Sam does not have one
I
available
wish
to
I
me.
did. Yeah.
Yep. Unless he was holding out and just lying to me would not be nice. You have a lot of capturability with it, but the expense alone is often enough to turn off our customers or make it really difficult to procure the solution or even just outsource this. It's a slow process. It's expensive. Sam brought up while we were talking about like some of the PPE requirements and what you need to do with the room to be able to set this up. So all of that becomes a huge limiting factor.
Yeah. The last possible solution, I was talking to Chris after this, was we could technically section the part, and we did speak to him, and he said, if you have to, you can section it, but we didn't want to do that. We didn't want to take the easy way out. Obviously, if you have a part that you can destroy by cutting it, well, then you don't really need to silicone mold it. We're doing this the hard way to hopefully show you how to do it so you can learn from our mistakes, successes, and copy this workflow if you have internal geometry that you can't just hack into.
Yeah. Yeah. If you can cut it, save yourself the headache, right? Join us on our journey. So, Sam, this was a great slide that you helped put together
Yes.
when talking with
Yes.
Chris. So, what was that conversation?
So, I spoke to Chris, when we were getting this project started, throughout the whole thing. I wanted to know why, he is the driving force behind this. And he told me a little story. So he polled, a bunch of these impeller parts and, looked at those 8 in total that they wanted to use for this digital ecosystem, this reverse engineering project. And out of those 8, only 4 of them were able to be successfully scanned with his scanning equipment. The rest of them had this internal geometry hurdle that, you can't get down in there. You can't see what's going on inside it. So 50% of the parts that he took aren't even able to be candidates for this digital ecosystem project. this project is going to be a very large initiative. There's going to be essentially replacing an entire warehouse with a server of digital parts that you can just click on demand and start manufacturing whenever you're ready. This is going to take 6 to 7 engineers per site. So, and they are going to spend at least 25% of their time. So, a quarter of their week is going to be scanning, modeling, creating this digital ecosystem to reduce the physical inventory. But if only 50% of the parts that you found can't actually be manufactured or can't be captured, well, that's leaving a lot of parts on the table, a lot of spare parts in inventory, and it's leaving money on the table. So that's why we want to identify, use this silicon molding technique to really get the most and use the scanners, where they potentially haven't been taken before.
So let's talk a little bit about the 3D scanning process. In this case, we needed to 3D scan as much as we could. So my goal was to capture the outside housing, which was pretty easy to do, capture top and bottom, make sure I have all of the geometry I need. In this case, there's a ton of different solutions out in the market. I recommend evaluating all of them, see what works best. In this case, I went with a blue laser system. One, I'm trying to create a repeatable process, something I can copy and paste do over and over. So using a blue laser scanner allows me the flexibility to deal with chrome parts, shiny um, if they're polished and things like that. So surface finish doesn't necessarily matter too much as long as it's not translucent. The other key benefit is actually here on screen. So the blue laser systems we have a single laser mode. What this allows you to do is actually get deeper into pockets that you can't normally capture. Again, I can't get my hand in there, which means the scanner is definitely not going to fit. But we are aligning this mold we're going to create to this impeller. So getting as much internal geometry as I can capture is going to make Sam's job later on when he goes to reverse engineer it a lot easier. And I want to be cognizant of that because this whole process hinges on me getting this aligned, getting the top and bottom aligned, getting the mold I create aligned to it, and then starting to reverse engineer it. So if we fail at this step, we're dead in the water. This is very crucial. So having a system like that makes it a lot easier. The other thing I wanted to keep in mind was we don't really have a lot of registering features that tell us where we're facing in space. So aligning the top and bottom is quite difficult. So using these targets is actually what allowed us to do some of that. So to be able to align based off of the targets, as well as some of the very few registration features.
Yes, and really with the scan of the outside, overlap, overlap, overlap. I can't stress that enough. Even though we can't get all the way down inside, we need at least a little bit so we can have a clue what we're doing when we try and mate the silicon mold together. So Jonathan did a great job getting the scan at the outside, and when we get into the silicon molding, you'll see how great of a job he did there as well. But yeah, overlap, overlap, and alignment, I can't stress those things enough, are really key factors that we found to be pivotal to this workflow. Okay, so once we've scanned the part, you can see we scanned it directly into Design X. What are we going to do with the scan data? This all depends on your workflow, and obviously for us, we took it all the way to the end of the line and made a parametric model. But with your scanning, you'll either have raw point cloud data or triangulated mesh. Depending on the scanner, it might triangulate it for you, and if not, you can triangulate it inside Design X. Now, if you're just scanning for inspection, you have the CAD model and you want to align them, you can stop. Use the mainly raw data, maybe, run the healing wizard or something, but you don't really have to do too much mesh editing. Now, if you're 3D printing, hopefully you've checked out, GoEngineer's YouTube, our YouTube. There's a ton of information about getting parts ready for 3D printing, and one of them is to watertight the mesh or fill all the holes. Again, if you need that, you edit the mesh, you're done. The longest and most complicated workflow is to make a parametric model, or make a model that you can actually go and make a drawing from, make manufacturing files. It's make CAD from the scan data. It's normally what people want, and they want a one-click easy button. And while Design X has some tools to make that faster, there's no one-click easy right now. So that is the process that we're working through during the reverse engineering process.
All right. So the silicon molding process. this was the next step after we scanned the outside, scanned as much inside as we could. This is the part I had no knowledge on. So I can't stress enough how much I appreciate Alex's and his team's help on this part of it. But the most important thing is prep, prep, prep. Get this right, spend a little bit of extra time. On the left-hand side, I'm filling in all of these kind of outlets with wax. The important thing to note is that this isn't like a little hole where we just plug. The actual top side of this inlet, as well as forward, is open. So I filled that as best as possible. I thought I was doing great. I, poured in this low viscosity silicone and I just see it like dripping down the sides. It got really bad. So this was really crucial. The other thing is, if you look in the center, this is not a smooth part. And it's not just something where I'm pulling the silicon mold out. It's also a case where I have to twist it out too, right? I have these veins in the bottom that are trapping it. So this was something that was really difficult to kind of overcome. Another aspect of it was there's these 3 through holes on the veins. So in twisting and pulling out the silicon mold, I had to be cognizant of the fact that if I get silicon in those holes, now I'm fighting against my ability to twist it out. I already have this rough surface that I'm fighting with and contending, but in addition, I would also have this extra silicon in pockets that I can't quite access or get out. So I wanted to fill this center outlet as well. So I wanted to leave enough of this keyway for me to grab in the silicon mold because that's a registrating feature. That's a feature that I can use to align. Yep, exactly, align this silicon mold to the actual part. Actually, I should say Sam did that part, but I was keeping in mind what he would have to contend with there. And then the last thing is, while these materials did not require mold release, again, I was already running into quite the challenge. So I wanted to use mold release because it doesn't hurt me, it can only benefit me. So in this case, I used a little bit. It's actually something that I had to be thoughtful about the distance because there were pockets I couldn't get mold release in. So one of the strategies I actually tried was I just kind of sealed it up, sprayed inside, and let the vapor settle as I rotated the part. So that was another kind of key piece to it.
Just overspray, overspray. Nice.
Yes, exactly.
Well, you use mold release all the time for scanning. If you have a shiny part, you can use it to dull that surface down. I know you use a lot of it for that application, but finally you're using mold release for molding. So finally you get to use all of that
Yep,
spray that
my
you have,
my first time using mold release for its intended purpose.
right?
So some of the things I'm doing here is this material is called dragon skin. One of the things I was contending with was it's very low viscosity. So it was just draining out of the part. I mean, it did not go on any of the surfaces I wanted. So I added some thickener just to increase the viscosity. The other thing is it's translucent. So while it's not glass-like, it is something that the scanning lasers can go through and penetrate. So I made sure to add some tint just to give it some opacity. If you know widescreen. The other thing I did was because it was a little higher viscosity, I thickened it. I actually leave myself a little bit of extra silicon to, with my hand, spread it on some of those undercuts and those sidewalls because that's going to be crucial to capture as much of that as possible because we can't see it in the scan data.
So Jonathan, I'm new to silicon molding myself as well. I have no idea what I'm doing with it. It looks like you got, 2 buckets of goo, you mix it together, add some color to help with the scanning. That all makes sense. You're wearing gloves. Looks like you're indoors. What kind of environmental or PPE requirements? How toxic is this? Is it like working with 3D printing resins or powder, or is it less than that?
Yeah, it's less than that. So with 3D printing powders, your concern is with it aerosolizing, getting up in the air, inhaling it. With resins, you can build an allergy to it. In addition, it is UV curing, and some resins are 1 part, some are 2 parts. So as soon as it's hitting table or just being dispensed, it's curing. And you almost have to chisel it off tables afterwards. So you don't want that on your skin. You don't want to breathe that stuff. In this case, with a silicon, it was pretty thick, so I didn't have much concern with it splashing. But if you're using something lower viscosity, eye protection, I use gloves because, again, it was quite a mess. So I wanted to be able to dispose of those gloves, put on a new pair, and use them. Uh, you want to have good airflow in the room. So this room is a, a small, medium conference room, but it actually opens up into a larger room, and the HVAC's connected, so I had a lot of airflow. And then another consideration that I was contending with was just keeping a tidy space. The other thing I learned in my research was that latex gloves can actually inhibit the curing
Ah,
process. So that's an Alex question for later, but it can inhibit the process. So I was using nitrile gloves, latex free, something that wasn't going to affect my process downstream.
Absolutely, yeah, but latex is gonna inhibit any silicone, so even if it's, like, near it, silicone will not cure at all. So definitely something to keep in mind, or even like sulfur as well. Sulfur will do the same thing, so if you use a sulfur clay, it'll cause the same, yeah, it won't cure. But silicone for the most part, you don't have much you need to worry about in terms of PPE. As long as you're in a well-ventilated room, like what you're working in there, Jonathan, is perfectly fine. It's not going to stick to anything. Silicone only sticks to itself. So if you spilled some on the table, you'll just peel that up after it cures, and cleanup's easy.
okay, nice. Yeah, seems pretty you know low risk, and like you said, it dries solid. It dries so it's not sticking to itself, sticking to everything. So fairly easy cleanup, and you can just throw it in the bin rather than with resins you have mixtures of resin and IPA that you've got to dispose of very carefully. So yeah, much easier to deal with than some of the other stuff we have to use.
And to answer John's question, vinyl works. Yeah, vinyl's fine.
Vinyl gloves as well.
Um,
Okay.
Yeah, just make sure you look at, and with all of our materials, there's a technical bulletin. It has the mix ratio. You want to make sure you thoroughly mix the same ratio of the A and the B that says, because if you don't, that it'll cause that to not cure as well.
Mhm. Yep. And this one was 1-to-1, which was quite nice. It made it easy. Here is a montage of me struggling. So this was my very first attempt, and we wanted to show this because there's a few things to call out. One, it took me a little too long to realize that if I remove the clay or the wax from the bottom and just run a flathead in there or a tool, I could actually push the mold uh, through and up while peeling it out. And so that's actually what I did with every single mold after this one. The second thing I did was this specific material. Uh, it recommends 4 coatings. The challenge is making something that is stiff enough that when I have it on the table and I'm scanning, it's not warping under gravity and causing deviations, but also still soft enough that I could fold this inward, twist, and kind of pull it out. So that was something to contend with. I coated with different colors because I want to make sure I have sufficient coating all over the thing. And the other part of it was Sam has not seen this part in person.
Ah,
He's reverse
understood.
engineering completely off of pictures, off of what I say to be true. So making one coating a color that was kind of our special color meant that when we go to look at the mold, it's okay, what part of the mold is touching the actual part and measuring it, and what is just extra overpour. So
Yeah.
we had our designated color that we're using as reference. So if I saw kind of one surface in gray and another surface in gray, I knew the impeller we were trying to capture was in between those two because that was what was poured directly on it.
Yeah. So, those areas where Jonathan and I have to jump on a Teams call and be like, oh, there's this piece on the silicon and, it looks like a critical feature. It could be, a bit of overpour or a bit of, spillage. I don't know. Do I need to model this in? And Jonathan can quickly check the mold and be like, oh, that is red. That's not gray. So that is actually the second coat. That's not a critical feature. That's not touching the actual part. That's just, essentially the silicon mold that can be ignored. So having all those colors, I think, was honestly one of those like quick tips that we want to share with you guys because it's not something that I would have thought of, but clearly, Jonathan doing it, um, definitely helped, the downstream application.
So we want to take a moment to address any questions at this point before we jump into the reverse engineering process. So let's take a look at questions. If you have any questions, write them in the chat, write them in Q&A. We have Alex here, we have Sam here, myself. We also have some other people from Octon. Guy is in the background, kind of keeping an eye on things. And then we do have Chris who submitted this project, and we're so appreciative too, because this was a really fun uh, opportunity to flex our muscles a little bit, kind of challenge our brain. So any
So
questions to address?
Yeah, the first question we got is actually we plugged the 3 balance holes. Will we discuss how you reintroduce those to the model? Ethan, are you talking about the 3 cutouts on the outside, or are you talking about the 3 essentially like small holes inside that were used to balance the machine or balance the pump? Um, so if it's the cutouts, that was pretty easy. Not too terrible of a process for that. Jonathan managed to scan on the scan of the outside. He captured one of those holes, and then the other 2 were plugged. I just modeled that one and then essentially reverse engineered and idealized it. So I patterned it around the other 2 times. If you talk about the other holes in the bottom that he plugged to help silicon removal, they weren't in the scan data. They were plugged, so we didn't capture it. And small holes inside. Yeah. Okay.
Yeah.
They
So
they weren't captured. So what I would assume is once you manufacture it, the balancing process is going to be custom each time you manufacture it anyway. So that would be a process that you have to do each time.
yeah, the other thing I will mention in regards to that was I actually left them completely open on the bottom side. So, they're all the way through. So I wasn't concerned about getting a depth off of it. It was just when we go into the reverse engineering process, it's here's the diameter of the hole. Let's just punch it all the way through through the vein. And so that was kind of the process we would take in a long term thing. The other part I want to add is that the clay came out pretty easy. It didn't harden or anything. So using picks to get it out was another process. And then I am not going to say live because I know Alex said not to try it, but I did check the melting temperature of the clay, and it may accidentally fall into like an oven at some point in the near future to see if I could further optimize this workflow.
There are clays that you can do that with. We do have some that you can. So
Yeah, there we go. So get a clay that would melt, and then have some type of oven or tool to heat it up a little bit. It also helps with the curing process. So there are some silicons I found that can cure faster with certain heat. There's also ones that the stiffness can be improved when it's heated as well. So all of these options where you introduce heat, just you may be able to use it for 2, 3, 4 different reasons to optimize your workflow.
Okay. And I think the next question, and then we're going to have to move on because we got a lot of content to present to you, is somebody asked, John asked if we could remind him of the additive manufacturing technology we used or in conjunction with this mold creation process. Jonathan, you were the one handling 3D printing. What did you use?
So so as far as 3D printing goes, I did kind of 3D print this in FDM, just have a cutaway as an example. But one of the key parts of this project, I believe, is that Chris mentioned they are looking to metal 3D print these pieces. So as far as their replicating process, so having an accurate model that is also full parametric so you can make design changes for additive manufacturing is important to that end goal. It's not just copy and pasting them, but it might be further down the line when they introduce 3D printing that they want to make some design changes to it for different reasons. So we specifically didn't like the end goal wasn't to 3D print it for us. I 3D printed a cutaway as a sample to show you, but ultimately I believe Chris mentioned the end goal was to 3D print it with a metal 3D printer.
Yeah. Yeah. So that would be up to, whoever is in charge of getting the parts from concept to a manufactured part. We're really handling the digital recreation of the part, and the file type for us is just parametric for full editability, but not really, we're not covering the 3D printing side of things in too much detail today. But yeah, so to kick off and keep the presentation going, I'll cover the reverse engineering process. Now, I will point out that I'm not going to cover the entire thing. Start to finish, it probably took me about 6 or 7 hours, split up over a couple of weeks, just doing it, as and when I had some time. Fairly quickly, using reverse engineered software, GeoMagic Design X, I utilize a lot of the tools in. And if you want to see a full start to finish reverse engineering workflow, check out our YouTube channel, check out GoEngineer's YouTube channel. There's a lot of content showing you and walking you through the start to finish workflow. I'm just going to show you some of the highlights. The first one, was obviously Jonathan scanned this part into Design X using a live transfer tool, live capture tool. But then I had to align all of these scan datas together. I used at least the outside scans. I did some of the pretty automated workflows, like picking points that are the same on scan 1 to scan 2, and then have it automatically best fit. And you can see doing this process is fairly painless, just picking 3 points from one scan to the next, hitting a line, and then running the healing wizard to just tighten everything up, clean up any irregularities. And then once that was done, I then merged this together. So I had one scan of the outside. Pretty painless. It's a very familiar workflow with most people. Now, aligning the other part, the inside, definitely required a little bit more finagling. I first had the scan of the outside, and then I did an automatic regioning. So in Design X, I can pre-select and analyze the mesh, and any flat areas come in as a plane region. Any cylinder areas, a cylinder region. Same with cones, freeform. All of these different surfaces and selections are identified as a colorful splodge or a region. I did this for both the internal and the external scan. And the reason I'm not doing it the way you saw it in the last slide is because the scan of the silicon is essentially like trying to, if you've ever read a book and then hold the book up to a mirror and try and read it, it's, everything's upside down and backwards. And this is the same case for the silicon. The inside surface of the silicon is actually the outside surface of the mold, and it was very confusing. The way I aligned all this is by picking a datum, or picking where I wanted my coordinate system to be. For me, I used the keyway and the alignment feature at the bottom. I created a reference vector or central axis, some planes, and some other alignment features on both scans. I then put them both in the same coordinate system and then ran a best fit to get it all tighten and neatened up. I didn't actually combine both scans, although I could. I kept them separate mainly because when I'm working on the inside, I don't want the outside to get in the way of my workflow. I could do view clips and things like that, but just being able to turn things on and off made the workflow a little bit faster. So that was the alignment.
Yeah.
Yeah.
Oh, sorry.
Go ahead.
I was going to say a quick note on this is that one of the crucial pieces, I could scan almost the top of the vein, but I couldn't scan the bottom of it. So the top surface you're seeing of the silicon mold is actually junk. It's just, the fourth layer of silicon. It's actually the bottom surface of this that correlates either with the top surface of the vein or an internal surface of it that correlates with the bottom. And the part that Sam needed crucially was the bottom face of that vein, which was captured by the silicon. So that's why keeping it separate was crucial here.
Yeah, we definitely had a few arguments over Teams about, what am I looking at? Send me a picture of this one specific area. But anyway, the next feature I like to do in any reverse engineering process, at least the first one I like to do, is the one that describes the biggest amount of surface area of the part. So for this, it was the external revolution feature. I made this is a pretty quick process. Honestly, didn't take too long at all because I used the revolution wizard in Design X Pro. I did this because essentially it's almost like a clippy. If you remember way back to the dawn of the internet, it's like, hey, I recognize you need to do a revolution. I just select the regions that I want it to make the revolution. It then does the sketching for me. It does the solid body operation to revolve, and it gives me an object. Now, is it perfect? No. It got me, I'd probably say 85% of the way there, and the remaining 15%, I just had to, make the sketch idealized. Again, I'm the engineer. I'm the one in control of it, so I'm not taking just what the auto sketch gives me at face value. I'm adding my own constraints. I'm making things parallel and vertical and adding all of these kind of idealized, perfect sections to the sketch so that it's easily editable, easily reproducible, and easily manufacturable. So that was the first sketch or the first feature. The next feature I'm highlighting is the most complex, and that was the inside captured geometry, where I'm utilizing the silicon scan that Jonathan made. I'm going about this using surface modeling techniques, and I'm essentially capturing all of these surfaces that were silicon, and creating lofted surfaces to capture the surface very accurately. You can see here, I'm verifying each step of the process is accurate by turning on the accuracy analyzer, so I can see a heat map of where the deviations are, if it's in tolerance, out of tolerance, or if I'm on the right track. Now, I'm taking the results from the accuracy analyzer with a bit of a grain of salt, because at the end of the day, it's a silicon. The silicon might have warped, or we might have a bit of scan data that is the second layer. So I'm essentially using the information Jonathan's giving me, as well as the scan data that I'm seeing in Design X, to kind of create this blended result where I'm idealizing it, making surfaces neat and tidy. And once I've made surfaces on all of the faces of this vein, and then trimming it all together, trying to neat and tidy it up. And you'll see here, once I've finished this, trimming of the surface, I have to do every single, if it's not just three sides, I've got to do the back side as well, where it meets up with the rest of the object. So trimming all of that together, I then essentially make it into one solid body of just the vein. And sure, I could then do the next process, do the exact same process again for the next vein, if I wanted the model to be as scanned. Now, I'm trying to do this a little bit more with engineering thought. So I'm going to idealize it and use the pattern feature. So I'm making one vein and that I'm happy with, and then I'm going to pattern it around 3 times to then give me the final model. And yeah, all the while I am checking the accuracy analyzer, making sure that the sketches, and you can see here on the left as well, I have a full feature tree, so I can go back and edit a particular feature if I need to. And also, when I'm finished, I can live transfer the whole thing over to SolidWorks, Inventor, whatever major CAD package I'm using. So it'll build the feature tree that I've made in Design X in my native CAD system as well. So, Jonathan, if you hit the next stage, you can see the results, the fruit of my labor. Probably about seven hours worth of reverse engineering. I did have to start again, because I kind of overlooked the alignment step. I brushed through it, thought I've done 100 reverse engineering parts before. I don't need to really take the time to get the alignment right. I skipped over it, started reverse engineering, did a few features, and then kind of realized that actually these two scans aren't aligned. I don't like it. I need to start again and I get this alignment right. So again, can't stress making sure the alignment is good before you jump into the project enough. And yeah, this is the final model. I'm pretty happy with it. I'm a perfectionist. There's a few things I'd want to change, but we're pretty happy with the result.
Yeah. The other thing I want to add and quickly highlight is Sam mentioned his accuracy analyzer a lot. There's a lot of art that goes into reverse engineering, especially off of scanned data. You have the part as scanned, which may deviate from your design intent. There's certain features you look at and you're like, no way somebody sat in SolidWorks or Inventor or some other CAD package and designed that, right? It's been worn, it's been beaten, it's whatever it may be. Maybe it was designed and you put into production and you're like, oh, this is kind of weird. And somebody was like, oh, this isn't hammer tolerance, and just whack it and suddenly it fits. You have to decide what you need to capture and how you want to make this. So he grabbed the one vein, he patterned it. So we actually see on the bottom left side of this that it's green, it looks nice, it's fitting to what the scan data says. And then when he patterned it, the one on the right is blue. It's saying that it's out. So keep that in mind as you go about reverse engineering, about deciding how you're going to do these types of projects, because that's where that comes up. Do you want to capture what is there, or do you want to capture and recreate what's supposed to be there? And again, keeping in mind what your final manufacturing process is, whether you're 3D printing it or casting it or whatever it may be. So just wanted to highlight that.